Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host for this podcast, and I want to thank you for taking the time out of your day to listen, and I think this is going to be a good one for you. I have a lot of people that are contacting me. They love the podcast, and they ask me, said, Paul, can you clarify continuous loads a little bit? Because some people have been struggling with this for years, and it's a good opportunity to sit down and explain continuous loads a little bit and kind of bring together the concepts of the 125% for continuous load versus 100% for non-continuous. And then there's this thing about 80% rule that kind of floats around in people's head, but the reality is the 80% rule is not in the NEC, because the 80% is actually the reciprocal value out of 125%. And of course, the NEC tells us what the 125% is to be utilized, but it doesn't really say anything about the 80%. So I think what happened with that is it's just a reciprocal value of 125%. Depending on if you know a specific value, then you can utilize 80% in order to be able to find out a value that you're looking for, depending on which way you're trying to go. Now, we're going to use 125% in our example, but then I might kind of sprinkle in there where people get this 80% rule. And again, it comes from manufacturers who have limitations on their devices due to terminals and their testing and things like that, specifically like circuit breaker manufacturers and what have you. Okay, but let's just kind of talk the continuous load in general. So Article 100 tells us that a continuous load is where the maximum current is expected to continue for 3 hours or more. Okay? And that's what we've got. So let's lay the baseline down. If I've got 50 amperes and whatever that appliance might be, whatever it is, if I've got 50 amperes and if it's going to be running at its maximum current, which is 50 amperes, for 3 hours or more, then I am to take that as a continuous load. Okay? Because that's what the definition says. We treat it as a continuous load. And then, the code says, when we do these continuous loads, that we take them at 125%. And where do we get that? Well, we get that in 210.19a1. We get that in 215.2a1. We get that in 230.42a. It clearly says that we take continuous loads at 125 and non-continuous loads at 100% of whatever their value is. So, before I make it complicated, and it does get more complicated, 50 amperes of load is 50 amperes of load. Whether the code tells me based on the condition of use or the use of it for 3 hours or more, or if the code tells me that that specific circuit or what I'm dealing with is to be treated as a continuous load. It's the code that's doing that. The load itself didn't change, right? 50 amperes is 50 amperes. That is my load. What the code does is tells us how to use that load. And we have to do some things because of that. We have to increase the size of the conductors maybe for that, or we might have to add that into our VA load calculation because of that, or what have you. We might have a water heater for in a residential that has to treat that branch circuit at 125%. Okay, so there's different things that the code tells us that we have to treat it as a continuous load. So I hear a lot of things out there. So that was the genesis of why we wanted to do this type of podcast. All right, let's kind of do some things that are given. Let's talk circuit breakers. And when I look at circuit breakers, I want to remind you of what it says, and let's just take branch circuits right now, make it simple. What it says in 210.40. Excuse me, 210.20. I don't know what I got, 210.40. 210.20. And if you go look at that, and I'm going to do this, and I'm going to get my code book here, and I'm going to look at it. And let's go to 210.20. Bear with me, I didn't have it open. I do a lot of this stuff from memory, so bear with me. All right, 210.20, which is overcurrent protection. All right, and reminds me, that says continuous and non-continuous loads. It says where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the rating of the overcurrent device shall not be less than the non-continuous load, which is 100% because that is what the load is, plus 125% of the continuous load. Okay, so that is under overcurrent protection. So in that scenario, if we have a circuit breaker, so a circuit breaker, let's say it's a 20 amp overcurrent device, inverse time, or just a regular old circuit breaker. The manufacturers will tell you that under normal use, that a circuit breaker is going to be limited. Okay, the maximum amount of continuous load that is going to be permitted on a 20 amp overcurrent device is 16 amperes. That's it. Okay? Now remember, the 16 amperes is the load. It's just classified as or signified as a continuous load, whether it's through the use or whether it's through something in the NEC tells us it needs to be. So, if I have a 20 amp breaker and I'm going to do it at 125% because we don't know anything about an 80%. That's not really in the code. We know that 80% is a reciprocal of 125, but we're going to use the 125. So we take the 20 amp rating of the device and you divide that by 125%. That is 16 amperes. Okay? So 16 amperes is the maximum continuous load. And remember what I said at the beginning? The load is the load, okay? 16 amps started out as a load. If it's a continuous load, it's still 16 amps. You just treat it as a continuous load. You with me? That is different than the conductor, which we'll talk about in a second, but that is the actual load, all right? So that's how you deal with circuit breakers and that type of thing, okay? Overcurrent devices, all right? Okay, if they have those limitations. All right, so that's the first thing. Now, the other thing is we're going to always assume here that all the terminals are rated at 75 degrees C. It could be less. You got to remember 110.14c will be an application if they're 1 gauge and smaller, 60 degree, but you typically use insulated conductors that have a higher value, so we're able to do this. So we are going to use 75 degrees C. Now, if you don't know what I just said, you need to go watch the video called Derating Demystified. Okay, you need to go watch it because in there I talk about all the things that I'm getting ready to go into now in more detail when you're doing adjustments and corrections for conductor sizing and all that type of thing. Okay, so let's think of this scenario. Okay, we've got a 20 amp overcurrent device. We know that if it's a continuous load that we can't exceed 16 amperes of the actual load, which we might take as continuous load. You with me? That's it. Okay, now that's 16 amps of continuous current, okay, for 3 hours or more, all right? You with me? I think you're with me. You're tracking with me now. All right, so that's where we're at. Okay, now, let's equate this to a conductor. So in our mind, we're looking at a 12 gauge. And me and you are so used to saying, well, in this scenario, I'm going to take a 12 gauge because I know that there's small conductor limitation rules in 240.4 that say that I use a 12 gauge on a 20 amp overcurrent device and I'm good to go, right? Now we know that doesn't apply to motors. We know that doesn't apply to HVAC equipment, but that's the general small conductor rule. We get it. We already understand that basic rule. Now, what about conductors? Now, another thing to remember, if we weren't doing continuous loads, if I've got a 20 amp overcurrent device and I've got 20 amps worth of load, then I could run 20 amps non-continuously through that 20 amp device all the time. So what does that mean? I could have 20 amps of load, okay? You tracking with me? 20 amps of load running through that 20 amp overcurrent device for 2 hours, 59 minutes, and 59 seconds and still not be considered a continuous load, and I could run 20 amps through it. The moment that I run 3 hours or more continuously at its maximum current, then it becomes a continuous load. Remember, in our case, the loads didn't change, okay? But could I run 20 amps through A 20 amp overcurrent device? Yes, as long as it wasn't a continuous load or something in the code didn't designate that load as a continuous load. You with me? You get me? I would feel gypped if I couldn't get 20 amps of non-continuous load out of a 20 amp device. I'm just saying, okay? I'm just saying. All right, now, let's move on. Now, let's say we're not in the real world. We're not in the normal world. And that brings me to something first that I want to talk about before I do some adjustment and corrections. Let's talk about table 31015B16, the ampacities. Now, I want to remind you, in 2020, that table is going to be 31016. You get to forget all this stuff about 31015B16. We've gotten so used to saying it now, it just rattles off our tongue. Now it's going to be 31016, as it always was, prior to the change cycles ago. And many old schoolers remember it as 31016 still to this day. So happy news for them, it's going back to that. But let's look at that table. So when I look at 31015B16, I want you to notice something. That table has 3 columns, 60 degree, 75 degree, and 90 degree. Now that is based on the insulation rating of the conductors that are utilized in the wiring of a building or a structure. And depending on its class or its temperature class or its nomenclature, for example, you see THHN, okay? If you see THHN under the 90 degree column, that means its T is thermoplastic, the 2 H's is high heat, and the N is nylon, that it has a 90 degree C rated insulation. Now, that is for use in things like adjustment and corrections. I can utilize that insulation's greater value for an adjustment and correction purposes. And again, you need to go watch Derating Demystified at youtube.com/master the NEC to get a more in-depth understanding of it. But we can use the value that's in the 90 degree column provided the conductor's insulation value meets those that are in this table. That means the rating is 90 degrees rated. Okay? All right, so we're doing that. Now, we can only use that 90 for this adjustment and correction purposes. So what do I mean when I say adjustment and corrections? All right, let me not go there yet. Let's look at this table again. See all these ampacities that are in here? You see them all? This is under 30 degrees C or 86 degrees Fahrenheit, and as long as I don't have more than 3 current carrying conductors, I can run these ampacity values right here continuously for infinity. And I'm never going to exceed the temperature rating of that insulation. This has been calculated like this way. These values here are the exact ampacities of these conductors. Okay? So that's something that people got to wrap their head around. For example, a 4-aught copper 75 degree is good for 230 amps. I can load that conductor to 230 amps and I can run that bad boy at that until the sun don't shine. Until my conditions of use change. The moments that those conditions of use change, then I got a problem because that ampacity starts to go down because now I am introducing things like mutual heating or higher ambient temperatures, and the ampacity heat is detrimental to it. So once that temperature starts changing, now that conductor can't handle as much current anymore because the current that's running through it, the heat can't escape, and now it starts moving that temperature up to the threshold of its insulation rating, and it could end up going higher than its rating. So under a perfect condition, we're not going to exceed the 90 degrees C, the 75 degree, or the 60 degrees C. But the world's not perfect, and we have all these other types of conditions of use we have to take into account. So that brings us to what we call adjustments and corrections. Now, many people refer to those as derating. Okay, you're not going to see the word derating in the code, but that's really what we're saying is we're taking conductor's ampacity and we're now going to derate it, drop it down because of a condition of use. Okay, now incidentally, it could actually go up and not drop it down if the ambient temperature actually is below 30 degrees C. Okay, you can actually, that cooling effect helps you get a little more ampacity out of it, but most of the time you don't have that luxury. It's going to end up going down. Okay, so how do we apply this? Well, the first thing we look at, let's just take some values and just use some values and pull them out of our head. Let's say that we have a raceway, and we're still with our 20 amp overcurrent device, guys. We haven't left that yet. I just want to put that aside. Let's say we have a raceway, and we're going to have 5 current carrying conductors in there. Now remember, we said that our insulation is rated for 90, so we're going to be able to use the 90 degree ampacity for adjustment and corrections. We know that it is a 20 amp device, and we know that the small conductor rules in 240.4 say that we're going to put a 12 gauge on a 20 amp, and we're going to protect the 12 with a 20. We get that rule. We're not thinking motors. We're not thinking HVAC. We're just thinking general rules right now, folks. So, okay, so we're thinking we're going to be in a 12. Okay, now, the problem is we know that we need to see whether or not this conductor is still going to have enough current carrying ability after I apply all of these conditions of use that are not the normal conditions that we would see in 310/15B16. Okay, so I've got 5 current carrying conductors. So when I've got 5 current carrying conductors, the first thing I need to do is remember I've got 90 degrees C insulation. Always remember that. Is I'm going to go over to table 310/15B3A, which is one page in front of 310/15B16, and you'll notice that 4 to 6 conductors are treated as 80%. So we want to turn this into a decimal, so that is 0.80. Okay, so we write that down. All right. Next thing we're looking at is say, well, you know what? It's not a perfect world. I'm running it in a location where the ambient temperature is going to be elevated. And let's just say that the ambient temperature is going to be, if we want to stay in, let's just go Fahrenheit for this one. And because the table gives you both, we're going to look at 310/15B2A for ambient temperature correction. And we are going to just use the Fahrenheit side. And we're going to remember that the insulation on the conductor we're using is rated for 90 degrees C. So we get to be in that column. So that's why we're in 90 degrees C. And we're going to say that the temperature was 105 degrees Fahrenheit. That is the temperature that we're running in. So I come down here and then I correlate it over to 105. And I notice that it's 105 through 113. And it's 0.87. So that is our 0.87. So we write that down. So we had a 0.80 for the number of current carrying conductors. That was our application that we applied there as an adjustment factor. That's called an adjustment factor. And then the 0.87 was a temperature correction. So that's the correction value of 0.87. Okay, so now what do we do? All right, we already know our breaker, okay? And we already know if it's a continuous load, then it can't exceed 16 amps on it if it's a continuous load. All right, we kind of went through all that. If it's not a continuous load, then guess what? I can put 20 amps on the thing. I don't want to rehearse that, okay? We rehearse or rehash? Rehash that. We already did that. So we're just kind of working through some math here. All right, so now, what do I got to do to take into account these adjustment and corrections? Well, because I'm doing this, and because my insulation is rated 90 degrees C, I can use the ampacity values under the 90 degree column for this 12 gauge. That's where we started at. We started with a 20 amp over the current device. We started with 12 gauge because of small conductor rules. We knew it had to be a 12. We're not dealing with motors, HVAC. We're just doing what we know. And in that scenario, let's look at 310/15B16. And we're going to say 75 degrees C columns because we do know that we're 1 gauge and smaller. If we didn't know anything else, we know that that would be 60 degree. But we already defined that our terminals and our insulation is rated higher, so we can use it at the 75 degrees C rating. So that's where we're going to be at the 75 degree. So let's go over here and is for our terminals. But we know that we can use 90 because the code says that we can do that for adjustment and corrections in 310/15. So let's go down here under 12 for 90 to see what we've got. Okay, it looks like a 12 is good for 30 amperes. Okay, so we're going to write that down. Let me write that down. 30 amperes. Okay, now again, that's under 90. That's not under 75. Under 75, we notice that it's only good for 25 amps. Okay, we get that. And we know that we have to protect it at 20 amps. You with me? But we know that we can use this 30 amperes for our adjustment and corrections. All right, let's kind of do that. So what the code says now, we're going to use some multiplication. We take that 0.80 and that 0.87 and we work this out. We do the 30 times 0.80 times 0.87 equals 20.88. And since it's a 0.8, 0.5 and major fraction and greater, then we're going to do that and round it up to 21 amperes. Okay? There you go. Now, what that tells me is that this conductor right now, after the adjustment and corrections, has an allowable ampacity of 21 amperes. That is after adjustment and corrections. Okay? 21 amperes. That's what that conductor is good for. Okay, so all I'm doing here is determining what ampacity is my conductor good for now. What is it at? Now, we already know that if it's a continuous load, then on the 20 amp breaker is going to be limited to 16 amperes anyway. Okay, we're already there. All we're trying to do with this one here for the conductors is to find out what our ampacity is of the conductor after the adjustment corrections, and what is the amount of current that we can place on it and not exceed its new ampacity value. Okay, in our case, if it was a continuous load, then we knew that the 20 amp overcurrent device was going to limit it to 16 amps. Well, can I put 16 amps on a conductor that's rated for 21 amps? Absolutely. Okay, because what is the actual load? The actual load is 16 amps. So this brings me into the 210.19A1B, and this is exactly what you do. You compare the 125% of the continuous and 100% of the non-continuous. If there's no adjustment or corrections, you take those values and you work with it. However, if there is an adjustment or correction, I have to do the calculation that I just did. And after my adjustment and corrections, I need to make sure that I have a conductor now that has an ampacity that can literally handle the load. And at the end of the day, what was our load? Our load is 16 amperes. We might take it as a continuous load, but the load itself was 16 amperes. Okay? So if you get where I'm going with that? So that's what we're dealing with. And so that's kind of how you work it. So explaining continuous loads and how you apply adjustment and corrections, it's really important to understand how they correlate. Because, again, if I'm just taking a conductor and I want to know whether or not how much current I can put on it, then, again, if I'm using adjustment and corrections, I just go to the 90. And then I'm going to multiply the adjustment and correction factor, and that's going to tell me what conductor's ampacity that I have. Now, that is my new ampacity, actual ampacity of that conductor now after adjustment and corrections. And it's got to be able to handle the load, period. Okay? So, there you go. In our case, like I said, if the 16 amps was a continuous load, that's the maximum load that can be on the 20 amp breaker, unless that breaker was actually rated at 100% rated for continuous load and non-continuous load. And that's a specialized breaker. Most of the breakers, for example, are limited to 80% due to the manufacturer's limitations. Okay, so that's kind of walking you through conductors and sizing. But again, the questions people ask are, if I've got a conductor that is, can I load a conductor to its ampacity? And the answer is yes, unless there's some other limiting factor involved. And that is a small conductor. So if I have a 12 gauge, if you look at 31015B16, a 12 gauge is good for under the 75 degree. A good is 25 amperes. And that is great to know when you're doing motors. It's great to know if you're doing HVAC, because 240.4 has an allowance in there to circumvent the small conductor rules in 240.4D. But otherwise, under normal uses, you're limited to a 12 gauge has to be protected by a 20 amp, a 14 protected by a 15, a 10 gauge protected by a 30, unless those other rules kick in. But all we're trying to do here is to see what our conductor has the ability for it to carry after adjustment and corrections. And if it's a continuous load, just to remember that the load is the load. Okay, and that's how you apply it when you're doing 210.19A1A and B. And again, it's the same thing applies in 215.2A1 as well. So again, 125% of continuous, 100% of the non-continuous. Okay. Not sure what else to talk about. I guess, again, remember that any load in a commercial building that is going to be 3 hours or more is treated as a continuous load unless the code specifically says that it's a continuous load. Okay? I am more than sure that I'm forgetting something to express it even better. Hopefully you get an understanding of that, get a greater understanding of wrapping your head around it. And as always, if you have any questions about it, you can always email me at info@masterthenec.com. you can go to our website. There's a little contact us button. You click it and you can type in an email to us through our internal system, and I'll answer your questions. You can post it on our Facebook page if you got a question. Don't worry about how dumb the question might appear in your mind, because it's not. Trust me, if you don't know or you question something, somebody else does, or maybe I didn't say something clear enough and you just need some clarification. I am not perfect, my friends. I am more than willing to clarify anything and talk about it in more detail until you get an understanding of it. And if I'm wrong, I want to know about it. You know what? I've been doing this for way too many years to be at a point where I think I know it all. I learned something new. Teach me something. I am excited about the prospect. Okay? So, if you do want to know more about applying adjustment and corrections and how all that works, then I encourage you to go over to our YouTube channel and watch that video, Derating Demystified, and it covers all of those adjustment and corrections. It even talks about 31015B7, the 83% rule that you have in the code. Covers that as well at the end of the presentation, or at the end of the video. It kind of goes over that really quickly. So hopefully that gives you some good information as well. All right, until next time, folks, stay safe. God bless, and I hope you got something out of it.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.